Thank you so much for inviting me, Dr. Agam and VIT, and the dear participants of this lecture on information theory and coding for image processing applications. I'm actually a professor of electronics and communication engineering, and my main research area is in image processing. And therefore, I have tried to highlight the application of information theory and coding, which is useful in image processing. So as you can see one title slide, in title slide, there is an image that says that some encoding has been done by using certain sort of coding and we get another output. This is just to highlight that the coding is also used, coding techniques are used in image processing. But before we move ahead to the topic, I want to tell you the information theory and coding is very useful area. And if you have studied the fundamentals, I'm told that you have already covered the fundamentals of ITC, that is information theory and coding. It's mainly used for handling 2 to 3 main features, especially in signal processing, data processing, and communication. One is the storage. Second is the time, that is processing time. So our communication time. And third one, which is very important factor that is associated with different coding techniques is the security. When you talk about information theory and different coding techniques for your digital communication system, it provides security to your message, security to your data. But when you talk about data communication, of course, it provides security, but it also provides benefit of the storage efficiency and of course, the time saving. So this diagram tells you, this image tells you, because you all people, we all use the digital images in computers. And we have seen that there are different data formats, image formats in which we write the images like JPG, JPEG. Those who are aware with MATLAB, this image is very popular for the MATLAB users. Lena image. So if you see the data format of any image, it's like JPG, BMP, TIFF. What is this JPG? Is actually a compression standard. It means when you actually see the image size or dimension as a 1 MB or 2 MB, actually that's a compressed image. So when you compress your image and you transfer to some other person through email, so the storage efficiency you obtain, and second, the time to communicate, time to transfer is also reduced. Of course, there are advantages related to security and privacy of your data. So with this note, and why I am giving this introductory note is you need to understand the importance of this course, importance of this area, information theory and coding. Today, or this era is the era of data, huge data. There is a huge data all across the world in every domain of engineering, science and technology. And the data is a big challenge. So in the entire data, huge data, the meaningful information is there in the entire data set or in the whole data. So it's very difficult to know and represent your meaningful data. And therefore, this information theory and coding plays a very important role. So this lecture has been divided into two important parts. One, I'll be talking about introduction to information theory and coding very briefly, because I believe that you have already studied this course. And second, I'll be highlighting the importance of information theory and coding in image processing application. It is not only used in image processing application, as I told you, it's very useful in all data communication, in all data processing, in signal processing, in communication tasks. But I will highlight the image compression especially. So when you see this slide, there is another image that tells you that how the image is being compressed. You see there is an original image, a grayscale image, whose size is large. The data requirement, the data dimension is large. Now, when you see the output image, which is the compressed one, data will be reduced. That is, size or the dimension will be reduced. So let's not go into the details at this stage. What you can see in this diagram gives some picture, some motivation that where is the role of coding? Where is the role of information theory? You see here, the first stage is, dividing the image or obtaining the image in small blocks, smaller blocks, 8x8, or you can choose other dimension. Then you are calculating certain DCT or any other transform you can calculate. Discrete cosine transform or discrete Fourier transform or any suitable way, transform you can compute. And the transform domain output is subjected to quantization. And then you go to, you find out which are the low frequency content, which are the high frequency content, which one you want to choose, which one you can suppress. It means what I'm trying to say, when you talk about compression, when you talk about data compression, you have to make sure that the originality of the message is not lost. The originality or the intelligence of the message is not lost. So you have to find out what are the redundant data. Where is the redundancy? And that redundancy that can be ignored, even then you can see almost correct signal at the output. So that kind of content has to be identified, and that content can be suppressed or can be, removed. So let's begin with information theory. This is one interesting block diagram you must have come across. It includes transmitter as well as receiver, because when we talk about, analog communication and digital communication, especially in context with digital communication, you find this the block diagram, transmitter and receiver. And you can see that you have a digital data. You get the digital data by using ADC. You sample, then quantize, then you apply PCM, you get the digital data. And then you have two types of encoders, source encoder and the channel encoder. And both have their, advantages and disadvantages. And both are equally important. You may use source encoding technique. You can encode your data into different format so that intelligence or security can be provided, and channel encoder has its own advantages. Then you modulate the signal, it goes to the channel. You know that in the channel, a lot of noise and interference are added. But I'm not going into the details of the communication, the noise, the channel interference. What I'm trying to tell you that if the data is digital data, in the digital data, if you replace the data by the image, the block diagram is common. And here also you can apply different encoding methods to your images. So what is important in, information theory is the reliable data, is the data which is very useful, is the data which is meaningful, that you have to consider, and other data you can suppress by using the different coding techniques. When I talk about data, the information sources are enormous. The data may be speech, the data may be voice, the data may be picture, the data may be an auxiliary signal, the data may be any continuous signal, physical quantity. So the data may be any kind of data, and that data, representation, data processing, and data communication. In all these areas of data, where you actually get the data, and in the data, what is there? Information. You can apply your information theory and coding technique. So here, if you see one picture, an interesting diagram is included. So what we can see in the picture, that there are cars, there are parking symbols, there are other trees, and there are two vehicles, and the different objects you can see. And all these objects represent certain content, and that content is the information. And when you talk about Shannon's theorem, it highlights, it talks about, it emphasizes on how to measure the information. And that is very important. You can have large amount of data, but what is important is information. And therefore, you know about this person. He has given a lot of theories. You must have read about, Shannon's theorem, that it talks about reliable communication using the information theory. And there is a very, very popular, expression by which you calculate the average amount of information. You all know it very well, so I will not spend much time here. This is how you calculate, where P is the probability of a particular symbol. And you know that more is the probability, the larger amount of information it will contribute. So his vision was like this: you choose a data, you take a data, apply source and channel encoding, and then subject to the channel. And reverse process can be applied at the receiving end. This is the basic. So where is the coding? Where is the coding, coming into picture here? If you see the block diagram, zip and CRC. So you can say here, you can go to the previous diagram, source encoding and channel encoding. So what we are doing, we are zipping it, and then we are using certain type of coding technique called as CRC. And the process is reverse while we are receiving the data. So as you can see, it very popular, example, like we use WinZip, WinRAR. So data compression is there. You can unzip by using source decoding. Similarly, error protection, as I told you, channel coding is mainly used for, to find out the error while transmitting the data, to ensure error-free transmission. So therefore, error protection is given by CRC code. Therefore, that channel encoding is done, and it has to be the same kind of coding has to be done in reverse manner while receiving the data. So there is one example in video coding. You see here, for video, MPG encoder is being used as the source encoder. What is our input here? Input is movie, that is moving images, picture, and here a RS code. And I believe that you have studied this course. So you must have studied these codes, RS coding and other codings, Huffman code and all that. So then you get your data in the form of CD or DVD. And again, when you want to recover, you can apply the decoding method, and finally it is broadcast at the TV. This is an example of cellular data. So cellular data means your data is speech. You can use any speech encoding as a source encoding method. You can use another encoding method for the channel encoding, and again the process can be reversed. This can be applied to the GSM or CDMA data or any cellular data. So what is this theory which you have studied that was proposed in 1948? It talks about the information theory, talks about measurement of information, source coding theory, and channel coding theory. So I am just giving a background. I'm just recalling that why and how this theory is used, especially in image processing application. Otherwise, I believe that you are very much, familiar with all these concepts. So as an example, you know it very well that there is a dice that you can toss. So suppose the toss outcomes are 1, 2, 3, 4, 5, 6. You calculate the probability, and by using the probability, you calculate the amount which it contributes. I believe you have studied this very, very well, that there is a probability of event, probability of certain incidents, and that contributes certain average amount of information in number of bits. Bits per symbol also, sometimes you say bits per symbol. When you say only amount of information, that is in bits, but when you say H, average amount of information is generally number of bits per second. So how does how does your information theory help? Let's see one example. Suppose you toss a dice these many times, million times, and you get these outcomes 1, 2, 3, 6, 2, 5, 4, and so on. You will definitely get certain outcome. So we know that how many outcomes are there? Maximum value is 6. So when we are talking about digital representation, 6 is the maximum value. So minimum number of bits in order to represent the outcome will be 3. But how many, how many times we are tossing? 1 million. So 3 million bits will be required to store the outcomes of all these events. And when you are encoding using ASCII representation, we know that 1 byte is 8 bits. So this is how it results around 8 million bits in order to store the complete outcome in this particular event. But the Shannon theory says that, or other coding theory suggests that we can even require lesser number of bits. Suppose we require only 2.585 as you calculate in Huffman coding also. When you actually require less number of bits, what will happen? These many total bits will be required. So there is the optimal compression ratio is 32. It means your number of bits required to represent the same data is less. You are compressing the data by using certain coding theorem that actually you do it. So when you compare the logic or the concept given by Shannon and WinZip and WinRAR, this is a comparison. A standard WinZip and WinRAR, you get the the compression ratio of 36.63, 35.74, and when you don't apply any compression technique, then there is no point of you compressing the signal. So this is another one example, one scenario, source coding theorem. When you talk about JPG 200 to 2000, so this is an image compression standard, MPG video compression standard, data compression, MP3 audio compression technique. So these techniques are, JPG 2000, MPG, these are the compression standards under the source coding. Similarly, under channel coding, these are different names like RS code is used for your picture transmission. Wireless communication, we prefer convolution code, but it's not only convolution code. I have just included one example. For optical communication, we use RS code as the channel encoding, so that, as I told you, error protection is ensured. Bit error, detection can happen, and you can protect the errors occurring in the bits. So I'm just coming to the end of first part because we have to complete the entire thing in around 1 hour or slightly more. So there are application areas where information theory and coding is finding its dominance. The emerging areas include communication, stock market analysis, economics, a lot of economical growth indicators, the assessment parameters are evaluated by using the information theory and coding. And you know that information theory and coding is associated with certain probability. So when you talk about there are probabilities of occurrences in any application, that area can find the, can use this information theory and coding. Then there are many areas like cryptography and other areas where this is used. So let's straight away go to the application in image processing and highlighting on, image compression. So why I have included this diagram is, again, in this title slide, the second part title, you can see one picture. For image processing, I think you all have some idea. Those who have studied image processing, they know it very well. Even if you have not studied image processing, it's very simple. When you capture a photograph using your camera, what happens? You capture the continuous image, natural photograph, store inside the computer. Once you store inside the computer, it becomes digital. Because when you put a cursor on that, it tells you 1 megabyte, 2 megabyte, because it has certain number of pixels in rows, certain number of pixels in columns. So it has number of rows and number of columns, and the smallest element of your picture is called as pixel. And all those pixels, the dots or the pixels, the smallest element in the picture, will have certain grayscale value. This thing which I am explaining is very important in order to understand how information theory and coding is applied. Let's talk about Huffman coding, how it is applied. And for that, you need to understand image as a data. So what happens when you capture the picture? How do you get the pixel intensity? That is actually the brightness value. So wherever on your face, same amount of light is incident, there the pixel values will be almost similar. So what I'm trying to say, in your picture or in an image, there may be many pixels having same grayscale values, same pixel values, same intensity values, same brightness values. It means there is a redundancy. And you can also say that there is a pixel value of 133. What is the probability? How many times 133 is occurring in the picture? So what I'm trying to say is the concept of probability, the concept of repeated occurrence, repeated happening, the frequency is coming here. And therefore, you can apply your concept of, the information theory and coding. So you know that how do you calculate the entropy? You know it very well that minimum amount of data that is required to represent an information that always carries some content, and in order to represent you get the average amount of information. And you also know that more here no uncertainty is there. Uncertainty is minimum, so entropy and uncertainty is related here. High uncertainty, so entropy is also high. You know it very well. It depends on your probability. This is one example. Suppose there is a coin which has only two possibilities, so the probability is 1 by 2. How do you calculate the amount of information that it contributes? Like this. So the relation between probability, the relation between entropy, you know it very well. So I will skip these things. This is also an interesting area. I mean, interesting slide where there is a ball, 3 bits per ball. There are three events, and therefore there will be 8 combinations. So how do you calculate the average amount of information from each or of each? It will be 3 by 8. So the ball is there, that is in the previous example. So 3 bits will be required to represent one ball, that event. So the degree of compression which you can calculate is 1 when both are same. And what is important is, I think there is some disturbance. I think I request all of you to get muted. So what I'm trying to say that suppose you are representing in other way and you see here, you require different coding, not like this coding. Then what you do that you actually require, it's not 1.5, it's 1.54. So in place of 2 bits, if you require 1.54, it means there is C by R, that is R is that, this C is the total code length and R is your optimal length. So you can see there is some benefit. It means the encoding method can help in eliminating the code redundancy. Now here you look at, this is another interesting thing. If you use the variable code, you know it very well in Huffman coding. You use the variable length code. You do not use equal number of bits in all the symbols. Otherwise, the actual amount of information will be used, and that is actually not required. So the concept is used also in image processing. Like you see here that in this case, after applying the Huffman encoding, we get it. Its equivalent entropy is 7.45, but you get its value as 1.07. And after you apply certain amount of more encoding, that is if the entropy value is 4.73, the value of C by R is 1.56. So what does it indicate? What I'm trying to say here is entropy matters, and the amount of compression and the type of encoding algorithm that you apply, that matters. And accordingly, C by R ratio changes, and C by R ratio indicates how much is the redundant data in the image, how much unnecessarily you are adding the data. This is a kind of application where you can see in the second image edges. Edges are high frequency contents. You can see the edges and boundaries of the picture. In terms of image processing, edges are called as high frequency, and they have high entropy values. Low entropy values, low frequency. Why I'm talking about this particular statement or giving this statement? Because I have mentioned here lower entropy value, higher entropy value. So where if you look at the second picture here, it's almost smooth. You see here, the grayscale value is almost same. It's completely gray. The difference is very less, and therefore the entropy is less. And when you see here, entropy is higher. Why? You can understand higher entropy values are there in high frequency content like this. Means high frequency contents where the contrast difference is more. And wherever there is more uniformity, low frequency content, though those are called as low frequency content, and they will have lower entropy values. So in the texture analysis or edge detection, you can group them, because if a particular area has same texture in terms of color, size or other parameters, you can group them and some redundancy can be removed. Like, there are 3 areas: smooth area, coarse area and periodic area. their mean intensities, their contrast, and their entropy. So you can find for a smooth area, entropy is less. For coarse area, entropy is 7.8. And for periodic, where the repetition is there, this is the medium entropy. So the reason for including all these concepts is to explain you the role of, entropy and the information theory. As you look at that, when you slightly change the image, this is one example where histogram is being explained. Histogram is nothing but a bar diagram that tells you the intensity distribution. You see here, these are the intensity values, brightness values, and the y-axis represents frequency. How many similar pixels are there? You see here, the second picture is looking more brighter, and therefore your histogram is widened. It's almost looking uniform because and here in the first picture, your grayscale values, your pixel values are centered at a particular point. So the distribution is indicated by your entropy value. Now, there may be lossless coding, there may be lossy coding. So what is lossless coding? When you encode, when you use certain number of bits to represent the data without loss of any information, we get what advantages we get? Speed up. As I told you, there is an advantage of reducing the time and of course the reduced storage requirement. Let's say a simple uncompressed video, there is a video of 500 by 500 pixels. If it is probably requiring 100 seconds over a capacity of 64 kbps, the resulting delay is very large. If your delay is 100 seconds and the data speed is 64 kbps, so speed is also very less because the dimension is very big. So what is the way out? You can reduce the dimension so that it will take less time and your capacity will also be not that much loaded. So the speed up is automatically obtained. The lossless coding is possible. Why lossless coding can be done? As I told you, until there is a redundancy, there is some similarity that you can remove or that you can ignore. Until there is a redundancy, you cannot compress. You cannot apply your lossless coding technique. So what are the factors because of which there is redundancy in the image? Correlation among the images, spatial correlation among neighboring pixels, similarity, some correlation is there between the two pixels. So rather than representing all the pixels, you can represent one pixel in the entire area. I mean, there is a method I will tell you. Temporal correlation among video frames, there may be temporal similarity and correlation between the two frames in the video, spectral correlation between the image samples. So the lossless coding is applied in compression of digital media imagery, your fax transmission. An example of such standards are like lossless JPG standard, your fax compression standard, your JBIG compression standard are the examples under lossless, but there are lossy as well. So as you can see this diagram with which today we begin, there is an original image. How does, how is JPG compression done? This diagram tells you there is an original image. You divide, you get the smaller blocks, 8x8 or even smaller or larger block. Why do we get? The reason is very simple. Very, very simple. If you take your entire image and apply the DCT, the processing time will be huge. So we do it in terms of choose a small block and we repeat the process over the entire image. Then what is the next? The next one is calculating certain transform. For example, DCT. Then you quantize. You all know the reason why quantization is used. Again, to approximate so that you can equivalently calculate entropy and you can apply your encoding. And finally, you get the compressed image. This is, the same block diagram explained in a different manner, right? Splitting, then applying 2D DCT. You apply certain uniform quantization technique. This zigzag means arranging your numbers in some sequence, either ascending or descending order. Then you can apply some run length encoding or then followed by entropy encoding and your image is compressed. And this is actually, the steps. These are the steps which are involved in order to compress your image. So where is the role of Your encoding, information coding here. Where is the role of your encoding? Here, right? So roll up DCT. Why do we use DCT? We can use other transform as well. So lossy JPG compression is based on transform encoding that uses DCT. In the DCT, what we have done, we choose a smaller blocks and then 2D DCT is applied to all those blocks. We calculate the DCT coefficients. And when you calculate the DCT coefficients, this is already done. You see what happens with the example. There is an image, you choose a smaller block, it has certain intensity values, certain grayscale values. But we do not work directly on grayscale values. So what actually we do? We compute the DCT and then I will come to that after some time. So how is compression? What is compression and how it is applied? It is used to minimize the number of bits required to represent an image. The actual number of bits which is required to represent gets reduced, like applications, your broadcast TV, your satellite TV, your military communication, aircraft teleconferencing, computer communication. Believe me, when you are sending your data, huge amount of data like images, videos, medical images, in the medical telemedicine is the area now in healthcare where a huge dimension of MRI or CT can be sent to the physician who is sitting in the modern hospital from the villages, from the rural areas. So it's a computer communication. There the compression technique is very much needed in the motion picture, in satellite images. Otherwise your system will hang and the processing time will be, communication time will be so much high that it will not reach and serve the purpose. So the lossy image compression, I think I have already given the description. So there are two types of compression, lossless and lossy. Most of the compressions are lossy. You cannot avoid, the loss of the information from the signal. Now, what is very important is if the signal is, the output, there is some loss, but your main content, which represents the meaningful information, must remain there. That much compromise can be done. And how do we evaluate that compromise? There are some criteria I will tell you very quickly. So as I'm talking about data and information repeatedly, there is a difference. You see here, data is not same as the information. Data are means to convey the information. Various amounts of data may be used to represent the same amount of information. Some part of data may not provide relevant information. That is called as redundancy. And that is not contributing any information, but the data is associated. So you can remove that. So this is how, the redundancy can be explained. And you see the first one, like N1 by N2 is the compression ratio where N1 is equal to N2. Suppose there are two data sets and N1 and N2 are amounts of data. So here both are same when you transmit and when you receive. So the second data set is same, compression ratio is 1. So the redundancy, that is relative data redundancy, you calculate like 1 minus 1 by CR will be 0 because there is no redundant data. But if there is a difference between the two, why I'm giving this example, when you compress, your N2 becomes smaller or where N2 becomes less. So when N1 is much greater than N2, your CR is tends to infinity. And when N1 is much smaller than N2, compression ratio is almost 0. It means N2 is very small and that's not possible at all. It's very difficult. So you can have different value of compression ratios and accordingly you can find the amount of redundancy. So in images, what are different type of redundancies? Coding redundancy, interpixel redundancy, psychovisual redundancy. I have been told that I have to complete by 4:10, 4:15. Therefore, I'm running quickly. So coding redundancy, as you can understand, you understand very well. Like you see here, you all do it. You know it very well in Huffman coding also. That these are the probabilities of occurrences of the data. Maybe these data are pixel values. And what you are doing, you are using same number of bits for all the events. And that, requires these many bits. But when you use the variable length coding, you see here, you are using actually the 2.7 bits, effectively 2.7 bits. So 3 by 2.7, the 10% is the compression ratio. How much you have compressed by using the coding. And this is related, why it is called as coding redundancy? This is related with coding. In your coding, you are assigning same number of bits to all the symbols or all the pixels. So that is not good. And entropy plays an important role here. I have already explained. What is interpixel redundancy? Interpixel means adjacent pixel values are highly correlated. Why? Actually, we do not have much time. Otherwise, you can ask me the question as well. You get an image because of two phenomena. One, there is a source of light outside. We are standing, sunlight is there. That light is incident on my face. So some amount of light is absorbed and some amount of light is reflected. So there is one area which is receiving same amount of sunlight. So the pixel values will be almost similar or same, and therefore adjacent pixel values have similar intensity values. So why to assign all pixels? Why to assign all pixels the codings? We can choose a particular pixel in a particular manner. Like this is another example where your histogram is almost same. It means the adjacent pixels have correlation. The third redundancy which is there in image is psychovisual redundancy. What is this? If the image will be used for visual observation, like a lot of information is usually psychovisually redundant. It can be removed without changing the visual quality of the images. There are two images you see here. In the first one, the data size is 0.5 KB. In the second one, 0.05 KB. The second one is the compressed one, but it is, it is affecting our visual capability. Visual capability is limited, but for machine understanding, this is not bothering, and therefore this redundancy can also be exploited. So I was telling you that how do you know that the compressed output has fidelity? You can calculate SNR and root mean square, PSNR, picture signal to noise ratio. If you obtain certain value of PSNR, you can compromise up to certain value of PSNR when you compare the input image and the compressed image, and beyond that you cannot compress. So there is a metric called as PSNR, and there are others which can help you in order to compress to what extent the data or the image can be compressed. So in generally in image compression, you have images, you apply certain pre-processing, then you quantize and you use the entropy encoding. This is something about the JPG quality, that if lesser number of bits are there, good quality. If the number of bits which are higher, the quality is even better. Why I am talking about this particular example is, remember, when you reduce the number of bits which are required to represent per pixel, it means you are compressing by using your encoding, maybe Huffman or run length encoding or entropy encoding. So what is happening? Quality will be always affected. Lesser number of bits are there. If you include more number of bits, the quality will be always better. When you compare a color image and grayscale image, do you know that when you ordinarily see the grayscale image, black and white image, one pixel is requires 8 bits. But in color image, there are 3 components each pixel have: R, red, green, and blue. So each pixel requires 24 bits to represent. So when you compare grayscale image and color image, you find that more number of bits are required and the quality is automatically more. So I have included here how the different steps work here. So what do you do? That there are certain number of pixel values, like in grayscale image, generally the highest grayscale value is 255. So the entire image you obtain by using the sampling and quantization, you assign, and then you obtain all the pixel values, their grayscale values, by using this process as a digital image. And then what do we do next? The resolution is also very, very important. If the resolution is less than the output device resolution, where actually we want to see, we can interpolate the extra pixels. We can interpolate the extra pixels, but that will lead the loss of quality. And if it is the reverse case, the quality is better. And in that case, some of the pixels could be discarded. So this diagram explains about that. And therefore, we go by a smaller block by block, so that we can check the redundancy. so that we can check the correlation, so that we can check the similarity. And this is why we do it by block by block. Then what do? We compute DCT, discrete cosine transform, or any other transform. So what happens, you know about DCT, we obtain, like we calculate Fourier transform of the image, all pixels, they will be converted into coefficients, Fourier coefficients or DCT coefficients. So the DCT coefficients represent your pixels. So what do? We begin with certain block, certain value, which is considered as a DC value, and other values can be compared as a lower values and higher values. Those are called as AC values in terms of, coding to the images where you apply the DCT. So what happens? This diagram explains you very clearly. DCT coefficients, we quantize them in order to approximate, and the quantized coefficients, then you see the probability. Suppose you see here 4 is there. How many times 4 is there? Accordingly, you can calculate the probability. And then when you want to recover your image, you can apply the decompression method. Like you see here that there is a block which is having a small area. These are the pixel values. How can we use it? You look at here that how does the Huffman work? I have explained with the help of first diagram. You know it very well. How do we get the Huffman coding, right? That there are so many probability values. You choose the highest one, and all those smaller one you separate. Again, you divide, keep on dividing, and finally you obtain the code. You know it very well. How it is used in images, you see here. Suppose this OETIR are the symbols. Symbols means they are representing certain DCT coefficients. And this coefficient is repeating 10 times. This is repeating 9 times. T is repeating 9 times. Assume T is a coefficient or your pixel. So what does Huffman code, or what is the requirement of Huffman code? You see here. This is the Huffman code of this. When you apply the Huffman code, you are not applying the uniform binary coding. Otherwise, maybe maximum number of bits is probably see here 6. So 6 bits will be required for all the symbols. I am saying different bits. So when you calculate the effective number of, total number of bits, you calculate like this. So hope you are understanding very well that when you use the different length codes in order to represent different DCT coefficients, then what happens? Your effective number of bits, which is required to represent the image, is reduced. Then this is another scheme, you know it very well. This is also applied in images. Like suppose there are 4 pixels or 3 pixels of which are having same values, and the pixel value is A may be 3 or 9, whatever. So you can represent A3, B1 and C4. So this scheme is also used in order to reduce the redundancy in the images. Like this is one example. How many times 3, then you write how many times 9. So you write 0 and 9. I'm sorry, 0 is for 9 times, 3 is for 1 time. And sometime you represent in the reverse manner also 1, 3 or 9, 0. So this is the diagram that again explains you compute the smaller block, calculate the DCT, you apply the approximation. Then I explained you that which are the components that can be removed. And therefore I talked about DC and AC terms. So your AC terms are high frequency terms, low frequency terms. Which frequency you want to keep with? Mostly low frequency components. High frequency components are generally not, useful, but you can do anything. Like it has been explained here, divide the image 8 by 8, transform the image using certain, transform, and that converts spatial domain into frequency domain. Some of you is interested. You can ask me that why do we convert our signal into transform domain? Why we are not directly in space, or directly not doing in a spatial domain? There is a reason for that. But I want to complete this. Then if time allows, you can ask me. Then quantize, then arrange the values in certain order. High frequency coefficients are more likely to be 0 after quantization. This improves the compression of run length in coding, and therefore you can ignore certain values. So this is how you can calculate the DCT and the DCT coefficients in between certain range. So this is your encoder block diagram, and this one is your decoder block diagram. You see that when you receive the compressed data, you are applying the entropy decoder, because the last stage was your entropy encoder. You use certain entropy tables. There will be a table. What is that table? What that table will include? Entropy values corresponding to different pixel values or the coefficients. Then you dequantize, because you have done approximation in order to bring into, so that you can calculate the frequency or repetition. Then you use the inverse DCT and you get the decompressed output. So the example is original ENA image 2D DCT. You see here in DCT, the advantage of transform domain is the intelligence of the message. The intelligence of the image is hidden. You don't understand what is output in DCT or DFT. But when you work in a spatial domain, you will always know that what is the result in the intermediate stages. So how do we work? We get the coefficients, as I told you. Then we convert them using some quantization technique, and we convert into some integer values, approximated values. This is the role of quantization. And then what do we find? Low frequency, medium frequency, and high frequency where? In the DCT output. And then like this is, this is how we convert the signal completely into DCT. And then we calculate, we use this method, and we calculate, we reach to this particular point. And then finally we get the frequencies. And as I explained here, this one you see here, when you have frequencies of different values, you can use a Huffman coding or other coding, and you can represent your data and reduce the amount of number of bits which is required to represent the image by addressing block by block. So you see here that your image, the actual image is this one, compressed image is this one. As I told you, for computer understanding, machine understanding, human visual quality doesn't matter. It doesn't matter. And therefore, when you compare frequency domain method and spatial domain method, your visual quality can be still better. But frequency domain method helps in computer understanding, computer way of representing and analyzing the images, and therefore there may be degradation in the quality of images. So original test image is this. You see here PSNR, as I told you, picture to picture signal to noise ratio 33.2 here. Here it is 32, so it is reduced, but the compression is this one. And when you have 2.44, it is further reduced. So you are compressing more, therefore there is a reduction of PSNR. Your signal quality will definitely degrade. When you compare 1 and 4, you will find that your PSNR is less because your compression is slightly higher. So more you compress, accordingly the PSNR is affected. So there is a fidelity criteria or the metric by which you can assess the compression technique, how well it is working, how good it is working. This is another example you see in terms of entropy. This picture 7.032 bits per pixel were used in order to represent this image. But when you see here 0.976 bits per pixel, what will happen? The picture quality is degrading, but of course it is compressed. Similarly here, if you take block size 4, entropy 4.348, the picture quality is like this. And when you apply fractal encoding with compression ratio 9.19, the picture quality is this. So if the compression ratio is 9.19, and when you increase the compression ratio, picture quality is again poor. The degradation is more. But what is important here, how you can apply fractal encoding. There is a important method, Jacquin's approach, fractal compression method, fractal image compression method, that exploits the similarity. Suppose neighboring pixels have same grayscale values, same pixel values. So you can compress that and you can choose a particular pixel. So that's called as fractal compression method. So when you use that kind of encoding with certain compression ratio, you get certain quality of the picture. So as I promised that I will be completing by, otherwise I wanted to extend very slowly to another 40 to 45 minutes. So I know that you have all attended different lectures today. So let me conclude that information theory and coding that plays significant role in signal processing and data communication or data processing. And the advantages mainly include that we deal with storage, we obtain storage efficiency, processing time is reduced, the communication time is reduced, and this is why, especially in data communication or in digital, processing or data processing, there the bandwidth efficiency is also obtained, because we know that when you are transmitting say 100 images and 100 images are in large dimension, so the utilization of channel capacity or the bandwidth will be, it will use more bandwidth and more channel capacity. So that efficiency is also obtained. So I think I will close here. I'll be very happy if I get few questions based on the topic. So this is one popular equation by which I always conclude my lecture wherever I deliver the talks. This is a different way of interpreting the Einstein's equation. Here M is motivation, C is commitment. So when M is constant, you can say E is proportional to C square. So my understanding is, in any task in your life, professional, personal, learning, teaching, whatever you want to do, if you see more is the commitment, more will be the excellence. If you do something, say C is half, so your excellence will be 1/4. And when C is 2, your excellence is 4 times. So when you are doing, with lot of you're putting lot of your wholehearted effort, then your excellence will be more. And remember, I just want to conclude with a good note. Success is an intermediate thing in your journey, but excellence is ultimate. So we all need to work towards the excellence. And for that, what is required is the commitment to whatever task you are handling, whether it is learning, teaching, or any other task. So thank you.